Okay, can you hear me?
Yes, sir.
All right. So actually, I want to cover. This is the last portion of this chapter. This is measurement of um, KLA, which characterizes the speed with which oxygen moves from the bubble to the liquid. So this is the KLA for oxygen. And actually, I started talking about uh, the the first method, but I think it's a good idea to give a very brief overview of how oxygen is measured. So, um, I mean, this is going to be very, very brief because this is supposed to be part of your practicals, which we will, I mean, I like to make it part of the practicals. But anyway, since it's unlikely that you will have practicals even in December, um, I'm just going to go ahead and give you a sort of a brief overview of what's going on. So, the basic idea is the principle. This is the principle of dissolved oxygen measurement. And like I said last time, the moment you see the word dissolved oxygen, it means oxygen in the liquid phase. So this is the oxygen actually dissolved in the aqueous or liquid phase. And the most common method, there are actually many, many ways, and new technology is coming up now. But the most common method is, I think, the one that was developed, if I'm not mistaken, 60s and 70s, is electrochemical. So it's the electrochemical method, and I'll so the basic idea behind it is basically um, oxygen. Essentially, the probe is a kind of a tube like this, right? Actually, I should show you the picture straight from the paper. So here is the picture. Um, is this visible to you?
Yes, sir.
Uh-huh. So basically, take a look at the picture on the left side. This is the most common one. So there is a this here. Uh, this is basically uh, anode and cathode embedded in a container, and it is at the bottom. So this is the membrane. I'm going to mark the membrane with a red color. So this is a membrane. Through this membrane, oxygen diffuses. So this probe is immersed into the liquid, and I'll explain the purpose of this membrane in a minute. Through this membrane, the oxygen diffuses to this platinum electrode, which I'm going to mark with a yellow highlighter. It's a very small cylindrical device. I mean, I don't know how to show it. Let's try green. So this disc here, which I have labeled in green, this is the cathode. And the oxygen actually, it's made of platinum, and how it works, I'll show you in a minute. So this oxygen kind of diffuses through the membrane, gets to the cathode, you know, where it is essentially, I guess, oxidized. This is the reaction that takes place. Sorry, it is reduced. So at the cathode, this reaction takes place. So oxygen receives two electrons. So it's actually the net reaction. This is showing you the two-step reaction. If you add it all up over here, what you have is essentially this thing cancels out, and you will end up with O2 plus 2H2O, right? Plus 4 electrons, so it gains 4 electrons to give you, I guess, 4OH minus. This is the sum total of the reaction. So, this is the net effect. Essentially, you're producing OH minus from O2. And at the anode, basically, I, you basically, there is chloride. There is a chloride sort of KCl that is used as so the electrolyte here is KCl, and this chloride sort of reacts at the dissolved chloride ions go, and at the anode they donate the electron. So the electrons essentially flow from the so-called anode where they're being deposited into the cathode. So this is the flow of the electrons from at the anode. The chloride comes and dumps the electron, and at the cathode, the oxygen receives the electron. And over a period of time, essentially, what you will find is that the KCl gets depleted because these chloride ions are being used up. So periodically, you have to come and replenish the electrolyte. So this is the basic principle on which it works. But I need to just tell you a little bit about why it works and what is the purpose of this battery over here. Why do you need this battery over here? So first of all, is this part clear? I mean, this is actually taken from this reference. The reference I should write down. I'm taking this material from dissolved oxygen electrodes, and this is by Yang and Sao. This is I guess from Lee and Sao. This is from, I think, sometime in the I can't remember the year now. Actually, it should be there in the it's sometime from the 80s, sometime from the 80s. This reference. So anyway, is the basics clear now? The construction clear? Move on to the electrochemistry part of it. Is the construction of the probe clear?
Yes, sir.
Okay, so now I just need to explain to you what is going on with that little battery over there. And that is explained over here. So this voltage that is applied over here is called the bias voltage. And this bias voltage basically, drives the entire process. So what this is showing over here, let me read it out to you, is that here is the key point. When an electrode of noble metal, such as platinum or gold, which in this case is the cathode, is made 0.6 to 0.8 volts negative with respect to a suitable reference electrode in a neutral potassium chloride solution, the dissolved oxygen is reduced at the surface of the cathode. So that's exactly what I told you. This electrode of noble metal, which is being referred to over here, this electrode of noble metal, this is basically the cathode. And if you make the cathode 0.6 to 0.8 volts negative with respect to a suitable reference electrode, which in this case, there is a reference electrode over here as well. This is your, I guess, there should be a reference electrode here too. So anyway, I think this would be if it is made negative with respect to a suitable reference electrode, in a neutral potassium chloride solution, which is what I showed to you. The electrolyte is potassium chloride. The dissolved oxygen is reduced at the surface of the cathode. Now, what this is showing you here in this graph, this is the principle on which it works, is supposing you take a gas of a fixed composition, right, and put it across this device, and you start increasing the negative bias voltage. You can see that the higher the bias voltage, the higher the output current for low values, right? So first it rises, then it becomes flat, and then it starts to rise again. Now, what's going on over here? What does this flat portion reflect? Well, once you increase the bias voltage beyond a certain point, so at the lower levels, the higher the voltage, right? The more the supply of electrons, the more the pickup of the electrons at the cathode, the faster they pick up the electrons because you're applying this voltage. So the signal keeps on increasing. But there will come a point when you're picking up the electrons so fast that essentially everything is limited by the supply of the gas. So essentially, beyond a certain rate at which if you increase this pickup of the electrons, this flux of electrons away from the cathode, if you make it sufficiently fast, then it is limited essentially by the rate at which oxygen is being supplied from here. So this is called mass transfer limited flux. And that's when it's basically picking up how much oxygen you have in the environment. So that is being shown over here. Essentially, what happens is that when you fix the negative bias voltage between 0.6 and 0.8, you can see that the current becomes independent of the bias voltage. And this is so because what the current is reflecting is the rate at which oxygen is being delivered to the cathode. It has nothing to do with the bias voltage that you're applying. It has become independent of it. And under these conditions, the relative current that you measure. So, for example, here is the current at 12% oxygen. Here is the current at 7% oxygen. Here is the current at 17% oxygen. And if you plot those numbers, so on the x-axis on the right-hand graph, you are plotting percent oxygen. And on the y-axis, you are plotting the relative current output. You basically get a straight line. So essentially, the height of this flat portion is a measure of how much gas you have. That's sort of the idea behind it. So is that part kind of clear? I mean, this is not exactly a detailed lecture on it, but do you get the basic idea?
Yes, sir.
I mean, any questions? None?
No, sir, was clear.
Mm-hmm. Okay, so with that background in mind, I mean, there's quite a bit. Um, uh, so maybe I should add a little bit here too, like why do we have a membrane and so on and so forth. So this is actually this thing, this device. This is actually called. I mean, most of the ones we have are called. These are polarographic electrodes. Um, uh, the presence of this membrane was done by a guy called Clark. So these are called Clark type electrodes. And the reason why this membrane, I mean, initially, so this is what is used to actually measure how much oxygen you have in your blood. It's the same electrode that is being used. And the reason why they introduced the membrane was that, initially, if there was no membrane, um, the electrodes used to get contaminated, right? I mean, you have basically dirty media. And in the case of blood, of course, I mean, you put this stuff into blood, and the next thing you know, all kinds of crap deposits on the electrodes, and the signal goes to hell in a handbasket. So it was Clark's idea to put this membrane. But this membrane actually also makes the whole thing work very well, because ultimately what is happening is that uh, because it is mass transfer limited, uh, essentially the flux over here, so the flux across the membrane, let's say if this is the membrane, maybe I should show that too. Is it shown over here? So let's say this is the membrane. This is the membrane, right? This portion is representing this line over here is actually representing. So this is the cathode on the left hand side. Way to the right hand side is the liquid in which the probe is immersed. So actually your probe is kind of like this. It's not allowing me to write. Here. So this is your probe with the cathode, and basically oxygen is this is the total cathode with the membrane on it, and oxygen from the liquid diffuses. And you can see that basically if the cathode is rapidly sucking electrons to the left, right, with oxygen coming here, and oxygen receives electrons from the cathode in order to get reduced. Basically, if you have a very, very high flux of electrons, what will happen is that the concentration of oxygen will drop to zero over here. And therefore, the flux of oxygen to this place will be proportional to the concentration in the bulk, right? I mean, you have, let's say, a linear drop across the membrane, and therefore, the flux of electrons over here, right? Which is actually I'm drawing it the wrong way. There should be flux of electrons going to the oxygen. This flux of electrons is directly proportional to the flux of oxygen, and the flux of oxygen is proportional to the concentration over here. That's the basic idea behind the dissolved oxygen probe. So that's the device that is used to measure the concentration of oxygen in the liquid phase. Now, with that background, we can move on now to how do you measure the. So we can go on now to the measurement of the. So what I told you last time was, I think I started doing it right. This is the dynamic method. First one is the dynamic method without cells. And the basic principle behind this method is you deoxygenate the reactor by passing nitrogen through it. So you bubble essentially nitrogen for 10 minutes or so until the nitrogen completely displaces the oxygen. So you have completely deoxygenated the liquid in the reactor. And this reactor is being operated under the same conditions that you will subsequently operate with cells. So you're basically doing this experiment with the hope that any measurements you make here without cells, the KLA that you measure will be preserved when you finally do the experiment with cells. So you're using the same RPM, the same gas flow rate, the same sparger, the same impeller, the same reactor, everything is the same. And then after deoxygenating it at time t equal to 0, you switch from nitrogen to air. And when you make that switch, it's intuitively obvious, as shown on the figure on the right, that when I switch from nitrogen to air, then essentially the bubbles, which were previously consisting purely of nitrogen, they will get replaced by bubbles of air. And from these bubbles of air, oxygen will be transferred from the bubbles to the liquid. And as that happens, your probe, which is measuring the concentration of oxygen in the liquid, will register an increase. That increase is shown by this white curve that I have drawn with decreasing slope. And the rate at which this is, how rapidly this goes up from CO to, as I mentioned last time, CO star, because I mean, ultimately, in the long run, when all the bubbles are full of air, right? All bubbles have air only, and they've been in contact. I mean, the liquid has been exposed to these bubbles for a long time. The concentration of oxygen in the liquid phase will reach CO star, which is a solubility when it is in contact with air of partial pressure pi a. So um, this speed with which it rises provides a measure of KLA, and the basic idea is shown on equation over here. Um, you have dCO dt equal to, this is from the mass balance, KLA times CO star minus CO. And this ROX is equal to 0 because this experiment is done without cells. And the CO star is essentially the final solubility of oxygen that will be reached in the liquid phase. And the initial condition that you have to use is initial concentration of oxygen is equal to 0, because what you're really after is what happens after you switch from nitrogen to air or oxygen or whatever experiment you're trying to perform. Now you can integrate this equation out pretty easily. I think I'll just give you the final expression. Um, so this is going to give you the final expression. So this CO, this is measured. This graph is measured with the DO probe that I just described. It's a probe that is sort of embedded. It's basically a probe. So it's like a probe like this that is embedded into the reactor with a membrane over here. And it's constantly sending a signal to the reactor. So you get a real time data that actually shows you what the dissolved oxygen is at any particular time. And the final solution, so this is just, this is just a digression that I made to show you how oxygen is measured. But otherwise, continuing, what we get is essentially ln. You can solve it, and you will get ln CO star minus CO equals ln of CO star uh, minus K L A T. This is what you're going to get. So, in other words, essentially what's going to happen is you're going to get some exponential increase. I mean, do I need to solve this, or is it pretty clear to you what's going on, right? I mean, actually, the correct formula is, or another way in which it's easy to see what's going on is you get CL over CO star equals 1 minus e raised to the power minus KLA times T. So this is basically as T goes to infinity, C goes to CO star. And maybe another way to think about it is if you write this term as T divided by KLA inverse, you can see that KLA inverse is basically the time constant, right? I mean, the bigger the value of KLA inverse, the more time it will take to reach CO star. Is that part clear? I mean, is the notion of a time constant known to you? First order process time constant?
Yes, it is.
Uh-huh. So KLA, then 1 over KLA, just like in a first order reaction, if you know you have dCdt equal to minus Kc, then 1 over K is a measure of the speed with which the reaction goes to steady state. In much the same way here, 1 over KLA gives you a measure of the speed with which the system goes to steady state. So returning to to this particular, so you actually get this solution, which implies this equation. And you can see that by basically plotting ln of CO star, if you plot, so this is the solution. I should just actually write it better. So this is the solution you get. This you can verify, it's a first order reaction. But that implies that ln of CO star minus CO equals ln of CO star minus KLAT. So that means if you were to plot, you got this data, the data is giving you CO versus time. If you plot ln of CO star minus CO versus time, and CO star is also known to you. This is, you assume that, the solubility is known to you. Then basically you can get the value of KLA as the slope. So it'll basically be a line of negative slope, and its slope is, the magnitude of the slope will be KLA. I just put slope is equal to minus KLA. Okay, so that's one way of estimating the value of KLA. But the downside of this method, the reason why downside of this method is that it is done in the absence of cells. And that's a problem for the following reason. So in reality, what you really want is, you want to know the speed of oxygen transfer while cells are growing in the bioreactor. Now, it is often the case that the cells that are growing in the reactor, they release products into the medium. For example, they could release butanol or acetone or ethanol into the medium. And that means that the medium is no longer the clear medium that you prepared in your feed tank. It's been modified by the products that the cells have released into the medium. Now, the modification of the composition by the release of these products, as I mentioned earlier on, it changes, the KLA. So one example is that, for example, A, which is the interfacial area per unit volume, depends crucially upon the surface tension. If you go back and take a look, the size of the bubbles depends upon the surface tension. And if any products are released that are surface active, then they will change the surface tension and A will change. In much the same way, this KL can also change with composition. So if you measure it KLA in nice clean water or nice clean medium, which is what this method is all about, and then simply extrapolate it to a real reactor where cells are growing, there is significant scope for error. And then this error primarily stems from the fact that the composition of the medium in the presence of cells has changed, and therefore KLA has also most probably changed. So what you want are actually methods that can be used in the presence of cells, not cell-free methods. These cell-free methods were actually taken from chemical engineering, where, ostensibly they work quite well. Actually, there's another one which, if I have time, I'll mention. It's commonly used. But the bottom line with cell-free methods is that they does not reflect, does not necessarily reflect the value of KLA in the reactor when it has cells. It has cells. So with that in the background, we're going to now look at a method. This is a slight modification of this method. This is also, I call it the dynamic. This is also the dynamic method, but it is with cells. So naturally, since we're looking at it with cells, this term over here is not zero. Okay. Since it is not zero, what do we do? So here is the equation once again. Minus RO times X. This is the mass balance for oxygen. Well, now this term is greater than zero. Actually, if it is basically, this term poses no problem if we knew what its magnitude was, right? If we know what it is, we're still fine. We can still find out KLA. Is that part clear? So basically, we need a grip on the magnitude of ROX. If we know what it is, then we're done. So the fundamental principle of this, so the basic idea, so the basic, it's the same thing really. In that case, ROX was rendered equal to zero. And in this case, the method will operate such that ROX is positive, but it'll remain constant. So basic idea of this method so this is to estimate the value of ROX first, and then apply the method above. So basically, the method above is basically looking at, so, we will come to a stage where we will, sort of switch from oxygen deficient to oxygen rich conditions, just like we did in the previous case. And the rate at which it goes up will tell us a little bit about, what the value of KLA is. But first we need to estimate the value of ROX. And so the way this is done is as follows. You basically, before you do the experiment where you try to find out KLA, you first do an experiment where you try to find out ROX. And how do you do that? So let's say this is the time t equal to 0. Okay. So let's say that I'm operating the reactor at some. So this is with cells. So the bioreactor is growing. At a certain time, what I do is I suddenly turn off. So here at this time, I turn air off. I just stop supplying. So this is while the cells are growing. I turn off the air. If I turn off the air, then the dissolved oxygen should start dropping, right? It will go down, and the rate at which it goes down should tell me something about this quantity ROX. Now, the key point here is, and I'll sort of flesh this out later on, you do not want the DO to go down too much, because, as I mentioned earlier on, there is a critical dissolved oxygen concentration, which I called CO crit. I did a numerical example saying that it is about 1/10 of CO star. You never want. So let's say if this is, some value close to CO star, you do not want it to go down below the critical value. Well, if you don't go below the critical value, then if you recall, I had made the plot. This is RO and this is CO, the dissolved oxygen. So if this is CO critical and I never go below CO critical, then that means that RO remains essentially constant, right? So the specific oxygen uptake rate, which is essentially how much oxygen the cells are consuming per unit time per cell or per gram dry weight, whichever way you want to take a look at it. So the specific oxygen uptake rate, this remains same throughout this decline. So in this phase, RO does not change. And that's because you never allow it to go down so low that it falls below CO crit. You stop. Let's say when it is at about 20% of, say, if this is CO, this is say CO initial, you will never allow it to go below uh, 0.2%. So you will never allow it to go below 0.2 times CO initial. That's it, 20%. You will never allow it to go below that, because if it went below that, RO might start dropping. That you don't want. So RO remains constant throughout this period. Also, the time scale of this is about 15 minutes. This entire section is no more than 15 minutes. In 15 minutes, growth rate is so slow, well, not slow, but it's too small a time for X to change. X also does not change. So neither RO changes nor X changes, which taken together means that QO is constant. QO is simply RO times X. Okay? And then at this point, I turn it on. At this point, here, I turn air on again. And then this will start to go up again. And it'll come back to its previous value, right? So it'll simply recover its previous value. Now, in the first phase, first deoxygenation phase, I call it deoxygenation phase. The first deoxygenation phase refers to this period from this first 15 minutes. This is phase 1. And this is phase 2. And this phase 1 is about, I don't know, 10-15 minutes, depending upon, and this is another maybe 10 minutes or smaller. Okay? So since RO and X do not change, during this period, you have dCO dt equal to KLA CO star minus CO minus RO times X, which is QO, but this is equal to a constant, right? And what do you think is the value of this term? I just want to see if anybody's paying any attention. What is the value of this term during the first deoxygenation phase? Anybody? I mean, I've turned the air off.
I guess it is the mass transfer rate of the oxygen which is going down.
Hmm. So actually, this term will be equal to zero. Because, and I'll tell
Yes,
you.
sir.
Let me first explain to you. This is a model assumption, really.
So just a second, sir, could you explain like the previous part once again? Like it was a bit not unclear to me.
Which part was not clear?
Sir, the part where where the differences arise when first you turn the air off and then you turn the air on again.
Uh, which part should I repeat? What didn't you understand? I mean, is
So
it
like
only?
so like basically the change in dynamics when like the air is off and then we turn the air on again.
That's right. So, I mean, so far all I've said is that when you turn the air off, right, suddenly you stop the air, right? You just don't supply any air. So now the cells are still consuming the oxygen, but you're not supplying any air. So, is it intuitively obvious that the dissolved oxygen will start to go down because the cells are eating up whatever was stored in the
Yes,
liquid
sir.
reservoir?
Yes, sir.
Is that part clear that the dissolved oxygen will go
Yes,
down?
sir. Yes, sir.
Uh-huh.
Yes, sir.
But the rate at which it goes down is what we need to know to really get to the heart of it. I mean, how fast is it going to go down? And well, the model assumes, and this is actually discussed in Doran in the section I have shown you. The model assumes that as soon as you switch, as soon as you turn off the air, right? Now, as soon as you turn off the air, they claim the supply of oxygen becomes equal to zero. That's what the model assumes. So the model assumes that basically, as soon as you turn the air off, the first term became equal to zero because you're not supplying any oxygen. This assumption is not quite right because you have all these bubbles that are still floating around containing air. And until these bubbles disappear, until they rise up to the top into the headspace and go away, until that time, still they will be passing on their oxygen to the liquid phase. So this assumption is not quite right, but this is assumption that O2 transfer stops immediately after we switch. We switch off the air. So far, so good. Yeah, I mean, we'll get to it. So actually, I should point out that a similar assumption is made over here, which is equally troubling. I mean, in the previous case.
So one more thing, so maybe I missed it, like because my internet connection hasn't been very well. So like, so in the first part, don't why do we assume like R naught X to be constant, or like why is it like so such that R naught X is constant?
In Actually, in this dynamic method with cells, it is constant because, well, you never allow the DO to go down below the critical value of the dissolved oxygen concentration. Well, so let me repeat. The critical dissolved oxygen concentration, which is approximately 1/10 to 1/20th of CO star, is the concentration below which RO declines with the dissolved oxygen concentration. That is shown in the figure over here. Now, if you never allow the CO, if you never allow the dissolved oxygen concentration to enter the low values shown in the red line over here, then essentially RO is independent of the dissolved oxygen concentration. It is in the saturating zone. So essentially the method never allows the dissolved oxygen concentration to go below the critical value. Is that part clear?
Yes, sir. Yes. Now it's
So now the second thing that I'm mentioning to you, that it is an assumption, it's actually problematic here also. Notice that in this method, I'm now going back and saying that the same problem that I mentioned just now, here the method assumes that as soon as I turned off the air, the supply of oxygen from the transfer of oxygen from the gas phase to the liquid phase stopped immediately. And I told you it is not true because the bubbles are still around, right? I mean, until those bubbles have risen up to the top and gone away, uh, oxygen transfer will still take place. Similarly, over here also, we are making a pretty drastic assumption. As soon as we switch from nitrogen to air, this model assumes that instantly all you have are air bubbles all over the reactor, and therefore you can apply this equation. But the truth of the matter is that when you switch from nitrogen to air, it will take some time for all those nitrogen bubbles to go away and be replaced by air bubbles that are actually causing the oxygen transfer. So there is a kind of a dynamic, an initial transient during which you cannot really assume that the model really applies. So I mean, this is discussed. I'll show you. I mean, I'll show you the it's this tricky business is referred to in Doran on page 22 as gas phase dynamics. But anyway, that's how the model works. Okay. Now, under the assumption that this is equal to zero, you can see that. So, and this is initial condition. This is done. Where is it? So, this has to be solved with the initial condition. CO at zero equals, I mean, I don't know, whatever is the value, right? Initial value. Let's suppose that it is equal to CO star, right? Suppose it's fully saturated. Actually, it could be less than CO star, right? It could be like, 60% or 50% of saturation values, whatever it is, whatever is the condition. So this entire thing is performed with a reactor that is running. Okay. So actually, I should call it, maybe the right notation to use is whatever is the prevailing steady state value, CO tilde. So this is prevailing steady state DO, dissolved oxygen concentration, in the reactor. So the reactor is, for example, running at steady state. Let's say the dissolved oxygen concentration in the reactor is CO tilde. So I should actually use this notation. This is CO tilde. This is the steady state dissolved oxygen concentration. Now at time t equal to 0, I turn the air off and CO starts to decline. But you can see that from this equation, which I call equation 1, since the first term is 0 and the second term is constant, all you have is dCO dt is equal to the negative of a constant value, which means that CO should decline linearly, right? So essentially what you have is dCO dt equals minus QO, right? And that means that basically, uh, if you solve it with this initial condition, you can actually see that all you get is the solution CO at any time t is actually the initial value minus Q naught multiplied by t, not Q naught. Yeah, sorry, Q0. This is RO times X. So essentially, in this phase, the decline according to the model should be linear. So this decline, let me show it in green color. This decline ought to be linear according to the model, simply because your cell density is constant, right? The cell concentration does not change. The rate at which each cell is consuming the oxygen does not change. That means the volumetric rate of oxygen consumption is constant. RO times X is constant. And if that is constant, then that means that essentially, since you're pumping in no oxygen to the liquid phase and simply consuming it at a constant rate, there will be a linear decline. And that linear decline, the slope of that linear decline, this quantity, this is simply the slope of the linear decline, right? And so the slope of the linear decline immediately gives you Q naught. So remember now, when I started talking about this method, I said that we need to know what is the magnitude of this term. And our first stage, during which we turned off the air and allowed the dissolved oxygen to drop linearly as it is according to the model, then the slope of the decline gives me Q naught. Now, once I have QO, which is the oxygen uptake rate, then I can go back to the differential equation and look at how it behaves during the second phase. So now I'm going to go to the second phase. Now that I know what the value of Q naught is, so now that I know, so this has yielded to me, so slope of the linear decline. So Q, this is how this gives Q0 or volumetric rate of oxygen. This is known to me now. Now I go back to second oxygenation phase. And now I will use the data of the second phase to pick up the value of KLA since Q naught is known to me. I mean, you see, the main problem with doing this in the presence of cells was that I had this extra term in the presence of cells, but we have found a way to determine it. Okay? And now that we have a way to determine it, I mean, we're good to go. So what do we do during the second phase? Well, see, there it is. So in the second phase, right? In the second phase now, again, the same differential equation holds. dCO dt equals KLA CO star minus CO, right? Minus Q naught, where this quantity is a known constant from the deoxygenation phase, right? We determined this in the deoxygenation phase. So how do I find out, the value of KLA? Well, one way to do it without integration is, so rewrite this equation as dCO dt, right, plus Q naught, right, and that is equal to KLA multiplied by CO star minus CO, right? So you already have this data giving you C naught, so I'll do it in red. I'm now talking about the data in the second phase, which is, man, what the hell is going on? I don't know. So this phase. I have this data, C naught versus time. From that data, I find out this quantity at every time, and then if I plot, um, so if I plot, actually, let me just show you. You plot on the y-axis, you plot uh, d co dt plus q naught, and here you can plot c naught. Then essentially you can get both. It will go down linearly. It will have a slope equal to minus KLA, right? And its intercept will be CO star. So this method actually gives you both KLA and CO star, where this data, right, and this data has been obtained from the data in the oxygenation phase, which is shown in red color. So once we have a grip on Q naught or QO from the first part of the experiment, then we can use the second part of the experiment to calculate, to estimate both KLA and CO star. Is that part clear? No?
Yes, sir, it is.
So just a question here.
Uh-huh.
So the value of Q naught will remain constant in the second oxygenation phase as well, despite us supplying more amount of oxygen in this phase.
Yes, because I mean, as I told you, right? I see. I mean, let me show it to you on this graph here. Yeah. Take a look at this graph, RO versus CO. I mean, maybe I will show you now. Let's take the green color. Basically, what is going to happen is, let's say, uh, erase this. So first of all, what are we doing? Let's so let's say my initial concentration is over here. This is my number CO tilde. This is the steady state at which it is sitting. Okay. This is, look at the graph on the left hand side and you can see my initial value is CO tilde, which is the steady state dissolved oxygen concentration before I start the experiment. All I'm saying is that during the first phase, right? So now I'll draw the path of CO on the CO axis. Starting from C naught, I come down to this point, but never allow it to go below CO critical. And then during the second phase, so here I go to the left, and then during the second phase, I just basically reverse the path and go back to the right. Now, whether I go to the left or I go to the right, RO does not change because it is in the regime where it is independent of the dissolved oxygen concentration. Are you following what I'm saying?
Yes, sir. And so the value of X will also remain constant when we start oxygenating.
Well, the reason is that actually it is growing, right? I mean, the cells are growing. But when the experiment lasts, the total experiment lasts only 10 minutes. You know, growth requires time. Cells don't double like every 5 minutes. Cells grow. I mean, significant changes of the growth rate, significant changes of the cell density occur over hours simply because the doubling time is on the order of hours. So if you finish the whole experiment in 10 minutes, the biomass concentration will not change. Are you with me?
Yes, sir.
Uh-huh. Okay. So that basically gives you this. So this is the most commonly used technique, the one that I have just done. This is also given the name um, gas in. This is also given the name gas in, gas out. I have no idea where this comes from. Maybe I'll give it some thought one of these days. But it is riddled with problems. I mean, the method is riddled with problems for two reasons, one of which I have already discussed. The first problem that I've already discussed is what is called gas dynamics. I mean, these see, ultimately what you're doing is you're using a model to estimate a parameter, right? We're using a model, right? This equation that we are using over and over again, this is really a model. And whether the experimental conditions satisfy the model or not has to be asked. And the first thing that is not satisfied is the fact that we are assuming that as soon as we switch, for example, from nitrogen to air, instantly everything becomes KLA times CO star minus CO. But the truth of the matter is that it will not be so, because when I switch from nitrogen to air, for some time I will still have the nitrogen bubbles lingering from the past. And therefore, this CO star, which I have assumed that what is this concentration CO star? Remember, this is the concentration that is in equilibrium with the bulk concentration in the gas phase. But the bulk concentration in the gas phase does not immediately become equal to that in air. I mean, for a while, you have bubbles that have pure nitrogen in them and bubbles that have air in them. So it's not CO star, it'll be something in between zero and CO star. But the model just moves ahead and says, instantly I have CO star at the interface because all the bubbles are containing only air. The nitrogen bubbles just disappeared. So this is discussed on page, so two problems. So two problems. So two problems with both dynamic methods, the cell-free as well as the the one with cells. One is the gas phase dynamics, which I have just described to you, that the model assumes that the conditions inside the bubble change instantly, whereas we know that that is not true. So this is discussed on page 422 of Doran. This is chapter 10. This is chapter 10 of Doran. You should read it. It'll give you. Okay. The second problem is the fact that you see uh, is basically time lag. So time lag, or maybe I should say response time of the DO probe. This is response time of DO probe. And what do I mean by that? I think if you've done a course in control, then you will understand what I'm talking. The DO probe actually does not immediately register the current dissolved oxygen concentration. This is because the DO probe itself takes some time to give you the reading. Why? Because as I mentioned to you, the oxygen has to diffuse across a membrane and get to the cathode. Now, this may take 10 seconds, 15 seconds. So, what you are measuring, the reading that you are registering right now, is actually the concentration in the aqueous phase 15 seconds ago. You're not getting real time data. You are getting data with a slight lag. This lag can actually have um, disastrous consequences for your measurements. So I don't want to get into the detail. You can read this. Let's see. This is discussed on page 420. This is discussed on. So this is section. This is discussed. So this is page 420, chapter 10 of Duran. So let me just actually open up Duran and show you what I have covered. And I urge you to read this on your own. Let's see. So what I have covered is this measurement 10.10 measurement of KLA. I have not done oxygen balance method. I'll get to this in a minute. What I have covered today is this 10.10.2 dynamic method. And the book has covers, as far as I can tell, only the method with cells in it. You can see that this figure 10.14 is showing you what I just discussed. This linear decline, this is actually theoretically what should happen, is what happens in the deoxygenation phase, and then the rise, this rise is what happens when you turn the air back on. So can you see that? Air off, air on. And can you call me later on? I'm busy right now. Okay. All right. So this is the air off, air on. This is the dynamic method. And here are I mean, they have done it in a slightly different way. You can read it, and so they have a slightly different formula, but it should. So I have used the differential method. I mean, are you in reaction engineering? Do you do the differential method and the integral method? Let me just see. Of estimating parameters. I'm just asking you, are you familiar?
Yes, sir, we're familiar with them.
So I use the differential method, right? Notice that in my notes, um, I never integrated it. I just used the differential equation itself to estimate the parameters. But I could go ahead and integrate this differential equation. And after integrating it, I could use this integrated solution to estimate KLA and CO star. That could also be done. And that is the method that is used in the book. So my method is the differential method. This is the differential. This is the differential method. Okay. And look at Duran. So look at Duran. Look at Duran. Page. I guess. So this is page 418, 419. 418, 419 for the integral method. And this is the formula you get. So she integrates it out. This equation 1057 is the one she gets. okay, where the CAL bar represents the steady state concentration, I guess, after you have reached steady state. Now, the the next part that I discussed was the problems with these two dynamic methods, and here she's discussing right here. This is electrode response time. Now she will talk about the problems you face because the probe does not give you uh, an instantaneous response, right? I mean, the response is obtained with a lag. And here she's explaining where the lag comes from. Because in a probe, the oxygen has to pass through the membrane, as well as perhaps a thin boundary layer outside the membrane, which she calls a liquid film. And these, lead to delays in the response. And the delays in the response, you see, what she's showing you here is that if you take a probe, let's say, and put it into a liquid with a given dissolved oxygen concentration, it does not reach it immediately. It takes some time to get to it. So this is what she's showing you in this graph. Notice that the curve is rising gradually and it's taking place on a time scale of about 40 seconds before it reaches its final value. So that means that approximately the time scale, this is the first order time constant, about 10 seconds are required before you know it starts to approach steady state. This is what causes a delay in the response of the probe. So this is what she calls right here electrode response time. Can you see that? Defined as the time taken for the probe to reach 63.2% of the total step change in the dissolved oxygen level. So anyway, because of these delays, uh, your method, any dynamic method, is prone to error. And the second part is the gas phase dynamics, where the models assume that things change instantly, whereas actually it doesn't, right? So this is discussed in this section over here. And finally, example 10.3 is basically giving you just it's a simple example of this dynamic method. It's giving you two time points and asking you to calculate the value of KLA from these two time points. So, if you want, I can go through it, but this is a simple application of that formula, right? I mean, KLA changes exponentially. So, you're given two time points, T1 equal to 5 seconds, T2 equal to 20 seconds. You're given the value of the dissolved oxygen concentrations. Just use the equation to calculate the value of KLA. Okay? So, please take a look at this. Now, I want to go back to something that I have not covered, which is actually at the beginning, and that is that because of these problems with the dynamic methods, what is of much more importance is actually the steady state method, which I can cover rather easily. I mean, the numerical part I will cover next time, but the principle is due to these problems. So I should say, due to these problems, due to these problems with dynamic methods. So one often prefers the following steady state method. So we're not going to worry about. So now this is the third thing that I'm covering. This is the steady state method. And the idea is now extremely simple because in the previous lecture, I did a, a, a mass balance on the oxygen in the liquid phase, and then I did a mass steady, and then I did a mass balance on the oxygen in the gas phase. And let me go back and show you that balance. Um, let's see. This is the liquid phase balance right here. This is the gas phase balance. Now, it's very easy to show you what's going on here. Now, at steady state, so maybe I'll show it right here. The idea is really simple. This is your reactor, and this is the flow rate Fg in, and this is the concentration Cog in, and then this is Fg out and Cg out, concentration going out. And what this is saying is that the difference between the two has to be equal to the rate at which oxygen has been transferred from the gas phase to the liquid phase. Yeah, I mean, so at steady state, if this reactor is being operated at steady state, then this quantity is equal to 0. And that means that basically in minus out has to be equal to the rate of mass transfer. If I can measure this quantity, and this quantity, then I can find out KLA. Sorry, I should correct myself. Where is the eraser? I should say so this quantity. So I know the rate at which oxygen is going in. I know the rate at which oxygen is going out by using appropriate flow meters and analyzers. And if I know CO star minus CO, then I can calculate the value of KLA. That is the principle, and this is covered actually in Doran right at the beginning of section 10.10 on page 414. So basically, this is on page 414 of Doran. So next time I'll finish this, and then I think we'll start. How many more lectures do we have?
Sir, let me check. Sir, 2 lectures, I think.
Oh, we have only 2 more lectures?
Yes, sir, because Thursday is Diwali this week. And yeah, Thursday is Diwali. Yeah.
So yes, sir, like only next week, 2 lectures.
Next week, 2 lectures, yeah.
Isn't there a makeup lecture on Saturday?
So you could have a makeup lecture on
So
Saturday.
you could schedule one on Saturday.
So I have to do it because I have to cover. Technically, I have to finish what are called fed batch and recycle reactors, and that will take me 1 lecture and maybe 2 lectures, and this will take me. So let me see. Actually, I prefer to spend less time on lectures and more time solving problems. Maybe what I'll try to do is to finish everything in the next lecture, and then keep 3 lectures for just solving numerical problems. Let me just point out that since the solutions are available on the internet, let me repeat it. I've already said it last time. Just do a search on your favorite website and you can find the solutions to the problems in Doran. It should not be that hard for you to go through them, right? You can collaborate, you can work with other people, you can tell your friend, you solve problem 3, I'll solve problem 2, share it, and then talk to each other. But you're expected to
Yes, sir.
solve problems. Is that clear? Because
Yes, sir.
once again, I'm not going to be asking you silly little questions about, tell me what are the different types of reactors, and it will basically be to take a numerical problem and dig deeper into what is your understanding of it. And once again, not just मैंने इसको इसमें डाला और इसको इसमें डाला और मेरा ये आ गया, right? whenever you solve a numerical problem, you also reflect on what it means. What does the number mean? I mean, are you with me? I mean, I think those who have gone through the Viva kind of know that I
Yes, sir.
probe a little deeper. So I expect some of the same to be the case. The numerical problems you are expected to do. I mean, if the solutions are available, I will do them. I will use 2 3 lectures to do at least 3 lectures worth of problems. This is what my goal is. So we have, you said 3 lectures total. Is that correct? I mean, uh,
Yes, sir, including the makeup lecture again.
Yeah, yeah,
uh,
including the
uh,
makeup 3 lectures.
so I will try to finish everything in 1 lecture and then devote 2 lectures to only numerical problems.
Yes, sir.
Um, and then I think then we are good to go. Okay, all right. So I'll
Yes, sir.
see you
Sir, one more
on
thing.
Saturday, I guess. Is that?
Yeah, yeah, Saturday, sir. Yes, sir.
So we
Yes,
will
sir,
go ahead
6th
and
November,
schedule
sir.
it uh, on Saturdays. Yeah, I like to keep my mornings for uh, my own work, so it has to be in the afternoon on Saturday.
Yes, sir. We'll schedule it. Yes.
3 o'clock or so. Okay.
Okay, sir.
Yeah,
Sir,
you were
3 to 4:30 then.
3 to 4:20, right? I think it's not one
Yeah.
and a half hours, but 1 hour and 20 minutes, right?
Yes, sir. Yes, sir. So, sir,
Uh,
another thing, sir. Can you please upload the marks on Moodle?
Actually, they have all been entered. I'm going to be asking my name. I asked the secretary to enter them into a spreadsheet. I'm going to find the way to upload them on Moodle today.
Yes, sir.
Uh-huh. It'll be
So
done
you
today.
could upload them on Teams as well if that is more feasible, because
Yes,
it
sir.
will be one
Because
same time.
yeah,
I
and sir,
mean, how
please.
do you how do you do
Sir,
it on Teams? I mean, are you just saying just put the whole spreadsheet there?
yeah, yeah, yeah,
No,
yeah.
no, no. I don't do that. I mean, I don't want everybody to see everybody's scores. I will put them on
Right,
Moodle
right. So
where on the.
then it'll be, yeah, it'll have to be done on something.
I just don't believe in making a public display of the scores. So the scores will be put in Moodle. Each one can see his or her scores.
Yes, sir.
And I do not know if Moodle provides the distribution. So if you doesn't Moodle automatically provide
Yeah, it
the
provides the average automatically. Yes, sir.
and distribution? So yeah, I mean, if you
No, it
want, you
doesn't
can.
give the distribution. So please give us the distribution. Yeah, that would be nice.
Okay, I'll see. I think GradeScope. I mean, I've used GradeScope in the past. I've not used Moodle. I'll see one of the two. Which one is easier, Moodle
Sir,
or
I guess
GradeScope?
Moodle is easier. Sir, also, sir, the thing is, the audit deadline is tomorrow. So many people wanted their marks to know if they want to audit BBL 331 or not.
Oh, okay. I'll release it today. Actually, I'll just tell the guy to do it today. I mean, if it
Yes,
really
sir.
comes, I'm doing it for the first time, uploading this stuff on Moodle. If everything else fails, then I'll find a way of emailing things.
So this is being graded out of how many marks? 30 marks?
30%.
Yeah, okay. And sir, so
Uh-huh.
the final major viva will be from the second part, post minor part of the
Huh.
syllabus, or will it be entire?
Yeah. I mean, I'm only actually. It all depends on what you want. I mean, I can do it either way. I mean, actually, let me be honest. There is actually significant overlap for the following reason. Um, in the next lecture, possibly two, if I can't finish it in one, I'm going to cover actually bioreactors once again. I mean, so what we have covered in the early part of the course is, we did batch and continuous reactors.
Yes, sir.
And what I'll be doing going forward is fed batch and recycle reactors, which are actually explained in terms of what happens in a CSTR. I mean, do you understand my point? Maybe it'll become
Yes, sir.
clear when I
I
do it. I mean, they kind of reflect part of what happens in a CSTR. So
yes, sir.
there's tremendous overlap, not deliberately, but it just happens to be the case. That's what this course has been changed. I used to teach everything on reactors in one shot, but people from the department wailed and forced me to split this into 2 parts. So that's where I stand right now. So even though formally there is no need, in practice you have to, because I mean, fed batch and recycle reactors, you simply cannot understand unless you know your CSTRs really well. So my suggestion is just refresh your memory, because you will not be able to understand this unless and until you know that. Is that part clear?
Yes, sir, that's clear.
Okay.
But it will be
Yeah.
after the minor. The syllabus will be after minor for the major.
So I will allocate 3 days. I've been told that the BTP and MTP presentations are, I believe, around the 17th and 18th. So I've been told by the head to lock 3 days in the week following the MTPs. I mean, do you know? Do you know what I'm talking
So
about?
isn't it
Dave?
27th and 26th? Or has it been changed?
What is on 26th and 27th?
Sir, the BTP meeting, I think. It was in a
No.
message we received from the convener.
When-
So
When did
because
you
so
receive-
17th are so 17th
Is
the
the
majors
majors.
would be going on. So BTPs wouldn't be possible, I guess.
Yes, sir. 15 to 24 is the majors.
Oh, okay. 15th. Okay. Then. I mean, I was given, like, he told me that only you better lock the dates right now. So why don't you go ahead and lock the dates, Dave?
Yes, sir. Okay, sir. I can talk to the. So should I talk to Professor Sundar and lock the dates?
I need 3 days. Of course. Most people have to spend only 20 minutes with me, so this is even better than a major, right? I mean, you have to spend only 20 minutes instead of 2 hours grinding.
Yes, sir. Yes, sir. It's much
So
better.
this is much better for you. In 20 minutes, you're done. So the last thing I wanted to check is, this is a core course, right?
Yes, sir. Yeah, yeah. But
Yes, sir.
this semester audit is allowed. Yes, sir.
Oh, I see.
One
Audit.
core is allowed, one elective or 2 electives.
So you can actually audit a core.
Yes, sir. You can. Yeah, yeah.
Yes, sir. So in the online semesters, the provision had been passed.
Okay. All right. Okay. Thank you. So
Yeah.
I'll
Thanks.
see you on
Okay.
Saturday.
Thank you, sir.
You can go ahead and schedule it, and you can also lock in the major days, 3 days.
Yes, sir.
All right. Okay.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.